Right. Good morning, guys. Welcome back. Before we begin, a couple announcements. So, I realized the Theorem project, although none of these questions exceed the scope of our study, the amount of algebra it takes to complete the project is tremendous. So what I decide is um you for certain parts of the question you don't have to do everything. I will give you partially the answers and you just do the rest. So that way you don't have to engage in the amount of algebra that it takes. All right. For example, for question 1, part C, D, and E, there are many terms that involves a quotient. So when you do the product rules, you basically have to do crazy amount of algebra, and that is quite not necessary for this course. And so probably I would just make you guys do one of them and then I give you the answer for the rest. So that you can do the last part uh, with much lighter duty. Hold on a second. Um, unsimplify. It may take me a while to figure your answers, but um, sure, if that's correct, yes. Uh, because it's hard to specify a specific form so that everyone follows. But basically, so for example, for partial x square, there are probably more than one terms, right? There are some second order partials and some first order partials. I will give you guys answers for some second order partial, some first order partial, and then you just do the rest. Uh, um, so if you have finished it, all right, you can have my answers as a check, all right, so check your answers. If there is something wrong, you would like to correct it, you can resubmit it, because if I remember correctly, I allow 3 submissions, right, in case you mess up with one submission. Of course, the last submission counts as your grade, so yeah. Uh, uh, I don't understand the question that we have to complete one section and email you to receive the other parts.
I think what he's asking is that, can you hear me?
Yes, I can hear you.
I think he's asking, like, because you said you're gonna give us 2 of them, we just need to do one. Like, what would be the process if you do one, and then how do you receive the other 2? How do we like send it to you and we're
No,
gonna
no,
get
no.
them?
So basically, I would post a file on Blackboard, hopefully by the end of the day, with the answers partially given. Right? So basically, you have answers. For example, for question 1, part C, right? You have answers for certain coefficient for certain partials, and you don't have coefficient for certain partials. I would just ask you what are the coefficients for those partials. Okay, so for example, I want you to ask what is the coefficient for partial theta, partial rho. You just compute that. Okay. Um. Yeah. Something like that. Something like that. Basically, I just want to reduce the amount of algebra you have to do in order to complete these projects, and I think that's not quite the important point for this course, because for this course I want you to be familiarized with the concepts and um the way to do multivariable calculus rather than just the really detailed algebra and algebraic operations, which
I
is
have one more question.
useful, but yeah, sure.
Are you gonna post the last lecture on YouTube?
Oh, for last lecture, I think there is something wrong with it, and I don't have the usually with the Zoom is automatic recording, and a it will send me the link for the recording, but for some reason for uh, last lecture I didn't find the link. I guess the Zoom doesn't automatically record my lecture, so
Okay, okay. I just couldn't join last Zoom. That's why I was waiting for the lecture
uh,
somehow to be posted.
I yeah I usually I would have the Zoom recording, but for some reason I couldn't have it. Sorry about that.
Okay, that's fine. I'll just use the notes. That's fine.
Yeah. Yeah. I have posted it the notes on Blackboard. I hope that helps. All right. Okay. So yeah, and I would probably give you some exercises on chapter 4 to prepare you guys for the third exam. So the third exam, the way I am proposing is to have a timed exam, and the exam is on Blackboard. It will only be available during the class time that day, and you just complete the exam and submit it on board. Uh, Rather than having a take-home exam like the exam two. All right. Uh, the format would be a lot close to exam one, basically a in-class exam. Uh, yeah, because it's online, uh, might not be many written questions rather than just a true or false, or just a fill in the blank kind of questions. Sorry, just that in that way, you know, both of us are having easier time. Um, yeah. So the exam would be on chapter 4 and chapter 5. So basically, vector value functions and double and triple intervals. So the homework assignment for chapter 4 and chapter 5 will count as extra credit for that. All right. Yeah. Yeah. All right. So, as in terms of final exam, the answer is yes. And if the department doesn't change anything, it would still be held on the schedule on the final exam calendar, which I believe is on May the 18th from 9 to 11. So May 18 is Monday. Um, yeah, yes. Okay. So today is lecture 20th on chapter 5.2. We will have 3 more lectures before the exam 3. Because this chapter is quite tight, I I am not confident that we will have an extra amount of time to do review session, but I can have extra office hour on Tuesday after the class time, and have a regular regular office hour on Friday after the class as well. So well, the office hour after Friday won't be any good because the exam is on Friday. But yeah, the extra office hour on Tuesday may be helpful if you would like me to hold that. All right. Um. So of course there is also an office hour today as well. Okay. In terms of take-home projects, I will give you partially answers for both question 1 and question 2. All right. So that you guys will have rather easier time. Yeah. Yeah. Um. Why do you want to email the projects to me before submit to Blackboard? I would really prefer you to submit it on Blackboard. That way, it's easier to keep track of. If tons of you emailed your project to me, and basically it just floods my mailbox, and I just lost track of it. All right. Okay. Let's get started. Mm, yeah, there were 3 attempts on Blackboard to submit it. If you mess up with the first one, there was a second one, and if you mess up with the second one, there was a third one. Um, if you mess up with 3 of them, I guess that's the time you email me. But yeah. Okay. So today we will be doing chapter 5.2. Right. So again, doing more double intervals. Okay. So remember last time, how do we define a function is integrable? That means how do we determine whether or not a function has a double integral? Okay. So remember, we have a concept called the Riemann sum. It's called the Riemann sum. So basically is when we partition this rectangle have a rectangle region. The x is from A to B, and the y is from C to D. Okay. Um. So yeah. So basically, what we did to get the Riemann sum is to partition rectangle into n by n terms with the same length, same dimension. That is, we partition the interval AB into n parts and partition the interval CD into n parts as well. And basically for each sub-interval, okay, we pick any point, but just one point. It could be any point. It's hard to draw them. And the value of f at that point represents the weight for this region. So the volume of the graph under this rectangular region ABCD is basically approximated by the sum of f of at the point Pij. That means that is the random point at the ijth rectangle. So basically ij here, multiply by the area of that small rectangle. Right? So remember, the double integral means you want to compute the volume of the solid that is under the graph of f over the region, over this rectangular region, right? So in this sub rectangle, right, you basically want this point to represent the value of all, the value of this point represents the value of all the points in this rectangle, so that everyone having the same heights, right? So this, in this cuboid, the volume is width times the length times heights. They all have the same heights. Of course, this is not the actual volume of this sub-rectangle under this graph, right? Because for the graph, it may have different values, but it's a close approximation, okay? And this approximation is getting better and better when we have a better and better partition, right? Because the smaller the rectangle is, you have more refined graph, and the difference is getting smaller and smaller. So this is called the Riemann sum, and if the Riemann sum converges as we take larger n, then we call this limit as the double integral. So that's how we define integrability for f over a rectangular region R by the Riemann sum. This is an analogous to a single variable calculus when we calculate the area under the graph, right? We do the same partitions, and then we calculate the area of each rectangles, right? So that is what we did before as a Riemann sum, all right? So let's invest investigate this more, all right? So of course, to compute the Riemann sum for every function is basically impractical, all right? That is not the way we do integration in the real life. Right? We just can't take limit every time we have a function. So instead, there are some nice theorems to tell us whether or not a function is integrable. Right? If you remember in single variable calculus, all right, if a function is continuous on a closed interval, then the function is integrable. Right? Continuous means integrability. And we have similar results in double integral as well. Right? So if you have a function that is so if the f is continuous on this closed rectangle R, then is integrable. Um, so to prove this theorem, you may need to develop some actual you know, tools, or um, simply we just don't have enough knowledge yet to prove this theorem. All right, so a key idea, if you're interested to look up, is called uniformly continuous. There is a result in analysis that says if f is continuous on a compact set in Rn, then f is uniformly continuous. And you need this uniformly continuity for f in order to prove the integrability over R. Um, so let's just, you know, take this theorem as a, you know, black box and just use the results, right? Okay. So another thing to look at is when we have a Riemann sum, for each subinterval. So if this is the subinterval Rij, we just pick any points, right? And you may wonder, does it matter if we take different points? Right? What if we pick the point, let's say Pij, and if we do the Riemann sum a different time, we pick another one, Pij prime. Would the difference of choice present a different in the limits? It turns out it's not. All right. To see that, you can look at it this way. All right. This is a closed region. The function is bounded. That means it will attain a max. And it will attain a min. All right. So if the limit exists, that means these two are getting closer and closer. Eventually, they are the same thing as your partition is smaller and smaller. So that means it doesn't matter what point you're picking. It's bounded between the minimum and the maximum. So in short, if you, let's say you pick minimum point for all the partition, we call it the lower the lower sum so let's say the lower sum n for f and we make the maximum the upper sum. And it turns out this, since the Riemann sum converges, these two limits converges. All right. So since any point in this sub rectangle is bounded between the lower limit and the upper limit, so that means any point is between L and F and U and F. Okay. So if this limit exists and this limit exists and they are the same, that means the the the, the limit for the middle one also exists and they are all the same. Right. So it turns out that the choice for choosing the point inside the each sub rectangle doesn't matter, which is nice. Right? We don't have to worry about it. So this is for integrability for a continuous function, but intuitively you may think that even though the function is not continuous, right? Maybe it's just a uh, uh, a collection or the disjoint union for each continuous subgraph, right? So basically, you're just breaking down into different parts, and each parts are continuous, although the whole thing is not continuous, right? An example would be you know um, something like this, right? Right here there is a there is a discontinuity here, but basically when you move it, when you look at this part, is it jumps on top, right? It's hard to draw it. Let me see if I can pull out the picture from the book. Right, the book has a big better picture. Something like this. something like this, right? Basically is, part 1 and part 2, they combine become the graph of f, but they are just discontinuous when you have a breakpoint here, right? They break from the sets here. That is called the set of discontinuities. This is similar to, in single variable calculus, you have a piecewise function. Basically, you have jump points, right? You know that from if you're familiar with Cal 2, that you can do integration just by breaking it into two parts, right? This is part 1, and this is part 2. Okay. And similar things can happen to double interval here, right? When you do the double interval of f over this rectangular region R, basically you do the integration on the first one here and the double integral on the second part here. And the integral of the whole thing is just you add this two interval up. So that means the function is still integrable, even though the function is not continuous for all the f. Right. So in this case, we have a more generalized theorem, right? Let's go back. It says that if the function is, defined on the rectangular region R, and the set of points where f is discontinuous, finite union of graphs of continuous function. So that means, right? You just break the graphs of f into a finite union of continuous subgraphs. Right? And basically the main idea to prove the theorem 2 basically relies on the fact that you can partition the region R such that the area that covers these sets of points where f is discontinuous have area 0. You can cover them basically with nothing. Right? If they don't have any area, right, the volume is area times height. There's no area to start with. That means they don't have any volume. So basically, you can just disregard the points of this continuity and computes the integrable over other regions, which are continuous. So that makes the whole function f integrable over R. Some counterexample for such example would be some function with jump points that don't have area 0. All right. So it may take you some imagination. All right. Basically, imagine you have a function. It's called Dirichlet function, such that is 1 on the irrational and 0 on rationals. Right. Such function is not integrable. Why is that? Because there are too many jump points for irrational numbers. That means you can partition this, well, let's say you just put it in 0 for integrate it over 0, 1, right? The close into 0 to 1, because the jump points happen so fast, right? You can't partition it nicely that separate all the jump points. No matter how small you partition, there are too many jump points under this partition. That means you can't have a nice height to represent the area under this partition, right? If you choose, let's say, a point that is rational, there are still irrational number in here. If you pick a point that are rational, there are also points that are irrational in this partition. And they are just jumping from 0 to 1, that makes the whole value not convergent. So when you look at the lower sum and the upper sum, they don't converge, right? The lower sum goes to 0, but the upper sum goes to 1. That's not good, right? Because we want the Riemann sum to converge. The Riemann sum to converge, so we can't have integral. Right? So that is the counterexample on, you know, having discontinuities that are not nice, right? In this case, well, in order for the theorem to be hold true, right, you want to have a nice set of discontinuities. Basically, the discontinuities makes the graph into finitely many continuous subgraphs. All right. Basically, the area of the part that are discontinuous having area 0. Right? You can think of a line having an area 0, a point having area 0. Okay. So that is for this part of the theorem. So there are some properties for double integral. If you're familiar with these single variable cases, all right, they are just analogous to single variable integral. All right, so you have linearity, this is for single variable. It basically, if you put it in double interval context, it's still true. Right? If you have a scalar multiple, basically you can pull out the scalar in front of the integral, right? This can also apply to double integral as well. Right? Why these two properties are true, this is just by the definition on, well, properties on limits. Right? Because Riemann sum is a limit, and limit has linearity, right? If you add these two and take the limit, it's the same as you take the limit for the first one, add the limit for the second one. Same thing for the scalar multiple, right? The limit of the scalar multiple is basically the scalar multiple of the limit. Right? That's not hard to see, all right, the first one and the second one. For the third one, right? Because when you look at the Riemann sum for a non-negative function, because it's non-negative, every point you pick in each subinterval will have a value greater than or equal to 0 as well. So when you look at the Riemann sum, this value is already non-negative, it's positive or 0. Delta x is also positive, that's how we define the length, the width. Delta y is also greater than or equal to 0, right? That's how we define the length of the subrectangle. So the whole thing is positive or 0. And you add a bunch of non-negative numbers, they are all non-negative, right? The sum has to be non-negative. So you have a sequence, right, of Riemann sums that are non-negative. And so therefore, when you take the limits, of course, the limit has to be non-negative. You can't have a sequence of positive number to converge to a negative number. That doesn't make sense. All right? So that's why when you double integrate a positive functions, it must the double interval must be positive or 0. So if f is greater than or equal to g for all the xy, for all of them, right? This is called monotonicity. Basically, one function is always greater than the next one. Then the difference of f and g, right here, must be non-negative, right? F minus g is always greater than or equal to 0, right? So when you use the linearity or property 1, you break it down into the double integral on f, subtracts the double integral on g. So that's why you have greater than or equal to 0 for this sum difference. So the fourth one is the basically the when you take the absolute value of the integral is less than or equal to the integral of its absolute value. To see that, basically, what it follows from here, right? A number is bounded, right? This covers the equal sign. Is less than or equal to its positive absolute value, and is greater than or equal to the negative of its absolute value. So for example, 2 is bounded by 2 and minus 2. Minus 1 is, of course, less than or equal to 1 and greater than or equal to minus 1. So when you have this upper bound and lower bound, you can bound it into the integral as well, right? Because you have the property 3, right? If this is monotonely smaller than this one, the integral of this has to be monotonely smaller than the integral of this, similar for this one. And for this one, for the lower bound, basically you can put the minus out by property 2. So that's why you have this. So the absolute value of f basically is positive, so it must be greater than or equal to the negative 1. So, but bounded below by this one. Make sense? All right. So that goes for the property for double integral. Right. well, there was a typo here. This should be a double integral. So basically, the properties for a single variable calculus, a single variable integration, also applies to double integrals. This a natural uh, transition or natural analogous analogy. So the last topic we will be covering is Fubini's theorem. So basically, well, intuitively, if you recall, last time we did uh, what we call a Cavalier's principle that says that in order to calculate or compute the volume of the solid, basically we slice this solid parallel to the xz planes, basically perpendicular to the y-axis, and in each cross section you have a area under the curve, because in each cross section the intersection between this cross section and the graph is a curve, and you have an area under the curve. We know how to do area under the curve by single variable calculus, single variable integration, right? And the area, the volume of the solid is basically you add these two all areas together. That is called the Cavalier's principle. Of course, we can slice this solid in the direction of the xz plane, which is perpendicular to the y-axis, or you can slice it perpendicular to the x-axis. These two methods don't make any difference. You just slice this solid into two different ways, but you should always get to the same volume, right? So that means, into a more rigorous form is called Fubini's theorem. Basically says the double integral is two iterated integrals. Right? You can integrate with regard to y while fixing x, and this becomes a function on x, and you integrate this function on x, and now you get the double integral. Or you integrate it over x, keeping y fixed. Now you returned a function of y, and you integrate over y to get the double integral. It turns out these two are the same. All right. To prove it, right, using the definition of Riemann sum, right? That's how we define integrability. To see that you can what you can do here is, when you look at how we partition this region R. Right? So when you add this Riemann sum, you can do it in two different order. The first one is by adding it row by row, followed by the columns, right? So you add these first rows together to get the first number, and you add the second one to get the next number, and so on and so forth. And then you add these numbers vertically to get the Riemann sum. Or, so this is this first, this second. Or alternatively, you can add each entries in the first column first, right? And add each entry in the second column next, all the way to the nth column. So you do it column by column. And it turns out these two adding up methods doesn't make any difference. So that is the general idea on why this theorem is true. Right? To prove it rigorously, let's look at the proof, right? So first, we know that the double interval exists. It's there. Right? So next, we want to show that this double integral is just iterated integral. Right. So let's prove that it is a dy dx. So first of all, we define a function x by keeping the x fixed and integrate f over cd. So in this case, fxy have the x fixed. So that means you integrate it over y. So next, we partition the integral CD into n parts. So by the additivity for the single variable integration, right? Because we partition it into n parts, the integral of the whole thing is just the sum of this n parts partition. You integrate it with the endpoints, in the partition. So in terms of graph, suppose this is fx. Right? The area of this curve is basically the area of these n partitions. You just add up this area together to get the whole area. So this is what we did here. So next we apply the integral version of the mean value theorem. The integral version of mean value theorem says that the integral of AB of fx is the same as 1 second. Let me make sure. Okay, yeah. This is small f. Some number between a and b multiply by the the length of this the interval, right? The partition. Why is it called mean value theorem? Basically, when you take the derivative on both sides, right, the left side becomes fx equals to f prime c b minus a. Well, this is well, fx from b to a, but that means fb minus fa. So this is what the actual, mean value theorem says, right? This is the integral version of it. Basically, you take the integral from both sides to get this part. Okay? So let's call the integral version of mean value theorem. So basically, you can find a point in this partition such that the integral can be represented by this value times the delta y. And in each part subpartition, you have that specific point. So to see in the picture, right, this is the integral. So basically you have a point, let's say here, right, yj star, such that this point times the delta y is actually the area under the graph. This is strictly equal. This is not an approximation. This is equal is guaranteed by the mean value theorem. This is equal sign. All right, so now you represent the f, the big F here, by the sum of, values of f times delta y. So now you put it into the integral of the big fx. Right? So that is the definition here. It's a fancy way of saying this. And from single variable integration, the integral is just the limit of the Riemann sum. Right? Because fx is a function on x. So we picked the point x in the subpartition and approximate the integral by the function on this point times delta x. So now this is an approximation, a Riemann sum on f. So this is not an approximate, but as the limit goes to infinity, this approximation becomes closer and closer to the actual number. Eventually, it converges to the actual number. So now you know that the interval exists. That is by the existence of double interval. So that means is equal to the limit of the Riemann sum. Of course, the Riemann sum can be rewritten using equation 1 that we just have. Basically, we replace fx here by a sum to another sum. So basically, in each Riemann sum in big F, there are also n parts of sum. Because this is equal, you can just replace everything by here, because it's equal sign. So let's look at the point here. Right? In xi, right, by the Riemann sum, xi is in between the subpartition in x. And when you look at the y is also inside the subpartition for y. So basically the point here is in the sub rectangle Rij. So this point is in Rij. So the this sum is actually the Riemann sum for the double interval. So this is the Riemann sum for this guy. All right. So we know that the limit exists. So the Riemann sum also exists, right? The Riemann sum also converges as the limit goes to infinity. So the Riemann sum exists, which is equals to the double interval. Well, on the other hand, this is the iterated integration from our construction. So that's why double integral is equal to the iterated integrals. Similar fashions can happen to the different order, right? In this case, we do dy first, then do dx. You can also do dx first, then do dy. Let's see how we can apply this to some examples. Right. So let's look at the function here. So now you have fxy is equal to x squared plus y. Okay, so in order to do a double integral on 0, 1, 0, 1, what you can do here is to find out what is the integral over y when keeping the x fixed from 0, 1. Right, while you keep the x fixed, you just have a function on y, right? The antiderivative of x squared plus y for y is x squared y plus half y squared. Right? So that is the fundamental calculus for single variable. And you are taking value from 0, 1. So Plug in 0 and 1. This becomes 3/2. Oh, sorry. Well, x squared plus 1/2. Okay. Yeah, x squared plus 1/2. And now you integrate it because this is a function of x. Now you integrate this x squared plus 1/2 over dx. Right, so the antiderivative of x squared plus 1/2 is 1/3 of x cubed plus 1/3 of 1/2 of x divided from 1 to 0 to from 0 to 1. So now plug in 1 here. You have 1/3 plus 1/2, which is 5/6. For 0, this is 0, this is 0, so minus 0. So you have 5/6. So that's how you compute a double interval by using iterated intervals. Each interval is a single variable integration, which we did before. Right? That is the fundamentals of doing integrations. Right? Another way of doing it is instead of having the function fixing x, how about we fix y here first? So now when fixing y, the antiderivative of this is, well, of course, for y is x squared y plus 1/2 of y squared. So when you take the antiderivative, when y is from 0 to 1, that becomes 1/2 plus 1, which is 3/2. Oh, sorry, this is when y is from 1, this is x squared plus 1/2. Y 0, this is 0. So now you have a function on, wait. Oh, in this case, we have to integrate it over x while keeping y fixed. So this becomes 1/3 of x cubed plus xy. And when you take the antiderivative from 0 to 1, 1 here is 1/3 plus y. So now you have a function on y here. So now you integrate this dy. So the antiderivative of 1/3 plus y with regard to y is 1/3 of y plus 1/2 of y squared. This is from 0 to 1. So you subtract 1. Well, yeah, you plug in 1 here. 1/3 plus 1/2 is 5/6 minus 0 plus 0, which is 0. So the result should be 5 over 6. And indeed, that is what we have. So it doesn't matter what's the order for you to do iterated integrals. You can do dx first. In that case, you keep everything else. You keep the x fixed. Then inside, you have to integrate over dy, which in that case you keep the y constant. Okay. These two ways of doing iterated integrals will get you the same answer, which is the value for double integral here. So that is the Fubini's theorem. Later on, this is only works for a rectangular region, right? The Cartesian product. But when we have a more general type of region for R, right? As long as it's closed and bounded, then you can also have double integral. And the way to compute it, it doesn't matter what is the order of the integration. You can do dx, then do dy, or you can do dy and then do dx. Fubini says you can do it the same way. All right. That is everything for today. Any questions so far? If there's no question, the class will be dismissed. And I will post this recording on YouTube. Sorry, Munjun, I haven't seen your question before. So basically, what I will do here is I will provide partially the answer, so that you don't have to do hopefully all the algebra, because the amount of algebra required to complete the project is too much. So I want to reduce the workload for you. You'd only have to do one or two things, all right? Uh, and then I will give you the answer for everything else. All right. Oh, the as for the homework, I guess you can submit it to me tonight. You can submit it to me by Sunday as well. Should be no problem. So I would extend the deadline for homework to Sunday as well, if that helps. Yes, the partial answers. Basically, I would put it as a hint. That would be posted on Blackboard as a supplemental materials. Um, I will try to post it by the end of today. All right.
Can I ask a question about the, are you still there?
Sure.
Yeah, can I ask a question about the Hessian in the Cobb-Douglas case on the
Sure.
case? So to evaluate that determinant, you get it all set up. It's a bordered Hessian, right? You've got the first partials of the constraint along the edge, and the second partials with respect to the function Q in the middle of the matrix, right?
So the constraint Hessian, right, is, it looks a little bit complicated. All right. So the first entry is always 0 because it only has one constraint. Right? So this is gx, gy, and gz because this is a 3-variable function. Gx, gy, gz here as well.
And in our case, the G is the cost function.
That is the constraint function, cost function, yes. Right. So for this 3 by 3 here, is not quite the Hessian.
Oh, it's the partials of the Lagrangian function.
Second order.
Right, second order partials of the Lagrangian function.
Right. So for example, for this one is fxx minus the Lagrange multiplier times gxx. Right. So for
Which
this one,
which is the same thing as hxx if h is the Lagrangian function, right?
yes. All right. So you can view it this way. All right. So if you put this is xx.
Yeah, I got this, but the question is, when you evaluate that, basically what we're going to do is we're going to calculate all those partials, list all those partials up, and then evaluate those partials at the point that we defined in the previous part of the question.
Yes. Because
That's what you're referring to as a huge amount of algebra.
The amount of algebra refers to compute the determinant for a 4x4 matrix.
Right. Okay, so there's no way around just doing the algebra, right?
Yes, because you need to compute the determinant for a 4x4 matrix in order for you to get the sequence of numbers for a Hessian criterion. All right, remember for Hessian criterion, you should construct a sequence of number and look at the sign of it, all right? Whether or not it's positive, whether or not it's negative.
Okay, so there's no way to do that other than chugging out those determinants one by one.
All right. Remember, for a 3-variable function with one constraint, the sequence has 2 numbers. The first one involves the determinant for this 3x3 matrix. This is called S1. Well, it involves in it. It doesn't mean it has to be like that one. All right. There is a coefficient usually refers to the nodes. All right. And the second number S2 involves the determinant for this 4x4 matrix. So you have to do the compute the determinant for a 4x4 matrix, which I think may be too much. So I would make it easier.
So the question is, I thought it was easier to do the determinant first rather than plugging in the, it doesn't really make any difference if you do the determinant on a function basis or if you do the determinant on an evaluated function basis, right? You can always
Yeah,
plug, you can always plug in the point later.
yeah,
It's easier.
You can compute the determinant before plugging it, or
Right.
you can plug it in, then do the determinant. It
But
doesn't.
because the point is a bunch of expressions, it's
Yes.
complicated to do it the former way.
Yeah, because it may be a little bit complicated because there are too many constants. You know, you have alpha, beta, gamma. Also, you have sigma, delta, and tau.
Yeah. It's a mess.
It
And
may
so
look.
there's no way to calculate the determinant of this. Like for example, in the previous question, you had all these zeros. You had all these zeros, so it zeroed out. You didn't even need to do the determinant. But
Yes.
as I recall,
This one, it may not be all zeros.
no, this is definitely not. So the
Because
question is,
it's not degenerate. Yeah, if it's all zero, it will be degenerate. All right, but it's
in
not.
this case though, because it's a symmetric, there's no way to take the determinant faster because it's a symmetric matrix or something like that, or it's got something
If you're
along those lines.
learning algebra, symmetric matrix means you have a positive eigenvalues, and the sum of eigenvalues is the trace of the matrix. There is a better way to play around the matrix, but I don't expect you guys to learn it. It's 260 materials, and simply it's just beyond the scope of this course, right?
Okay, so we got to turn it out.
Yeah. So then it's basically algebra, and it's just too much.
Okay.
I really hope you to grasp the concept rather than doing too much algebra. Some algebra is fine, but too much is, I don't think it's necessary.
But what would be really good if we have the intuition behind that that second derivative test using the Hessian, which is
Yes. I want you to compute the Hessian, right? Of course, but to
okay.
actually compute the number, this too much.
All right, thank you.
Oh, okay.